Hey y'all, it's Andrew Couch here, and in this Tidy Tuesday video, we're going to be going over dimensionality reduction methods for machine learning. So with the actual model that I created in season 1, where I was predicting UFC fights, we were dealing with a lot of features. Specifically, we're dealing like over 200 features. Additionally, with all the features that I created, we're moving averages, auto-regressive features. We were combining a fighter's data with the opponent's data, and they all shared the same amount of features. So we can see how that in itself doubles our actual features that we're going to be utilizing. So one of the questions I actually got in the video when we're doing a bunch of feature engineering is, how do I know if a feature adds value to the model? How do I know if the model actually works with these features? And how can we reduce the amount of features we actually use, especially when we're dealing with like highly correlated values? So I actually went back and revisited the actual modeling, the modeling for both the component models, where we were trying to predict like strikes landed, knockdowns, submission attempts, etc. I also created a actual like outcome model that would predict probability of like a knockout, TKO, decision, etc. for both parties. But for this video, I figured we just focus on just one model. In this case, I think predicting strikes landed probably makes the most sense, just because one, it was one of the more stronger features into our actual outcome model, and two, it's more intuitive, and the actual range of values is pretty large, whereas like knockdowns, there's usually only about 0 to 5 or 0 to 10 knockdowns. Actually, probably not 10 knockdowns, but you get what I'm talking about, where there's gonna be way more strikes landed, and it's way more variable than these other features. So I actually have wrote this script out, and I don't think the coding part is really that important, because first of all, there really isn't that much coding. It's more about just what commands we can think about using in our own problems. So I'm basically loading in some of our data that you're going to use to create our model data. So we have fight data, some fights, and a fighter table. I don't use all of it. I think I could probably remove the match data if I want to think about it. But right now, what we're trying to do is we have our fighter data frame, which contains each fighter's basically features that we've already created. So like the average strikes, knockdowns received, their previous history and stuff like that. Significant strike, lagged features. We also have like takedowns, total losses, total strikes avoided, win by what type, and their elo, and then their elo change from their past fight. So what we're gonna have to do is, one, we want to remove any data leakage. So in this case, it has like results from the actual fight, the round finished, and that stuff we don't really want, because it'll kind of cause issues with our actual model. So we're just gonna remove that. Additionally, we're also gonna rename them. So we're gonna basically take our data frame and basically join it with itself, because each row of the fighter data frame represents a fighter. And if we actually go back and look at our fight PK, we can see that we have basically 2 fight PKs. So we would want to join Cyril Gahn with Rosenstruck together, right? So I basically did that, just a basic join. And as you can see, with the actual data, I just selected the fight PK, which represents the actual match now, the fighter, the opponent. And then with their actual fights, we can see it's flipped too. Cyril Gahn is the fighter, and then Cyril Gahn is also the opponent. And then we can see just at the sanity check that when Cyril Gahn is the fighter, his average knockdowns is 0.5. When Cyril Gahn is the opponent, we can see the opponent's average knockdowns is 0.5. So right there, we know we have our data. It's nice and labeled and prepped for what we want. We also have this little target strike landed, which is the thing that we're trying to predict. Okay, so if we're actually looking at this, we have 2 fights, and they're essentially the same fight. They're kind of switched around. So in this case, I wanted to basically group by each fight PK and just sample one fighter's perspective from each fight. I definitely think you could probably leave this as is, but just just to make sure nothing crazy is going on, we're gonna switch it around. So just from a baseline, we can check our model data columns, which is about 282 features. And that's a lot of features. If I was using linear regression, there's no way I would use a linear regression model because, one, we're dealing with a lot of correlated features. Two, our actual amount of parameters we're going to be estimating is definitely likely to overfit. So how can we actually, reduce the amount of features that we have to make sure that, we're making an efficient model? I'm not going to go into like all the actual feature engineering that I created. So I did a lot of like fighter head-to-head features, such as like, whether they're the ego scores are greater or lower, the ego differentials. I also created some striking metrics and some strike differential metrics and stuff like that. I don't think that's too important for this this video, so I'm just gonna leave it as is and just kind of go as like a brute force approach, where we're just gonna have the default UFC data without any actual intuition or knowledge behind the actual sports itself, which is probably not the best idea when you're doing a side project. It's generally good to put in your own prior knowledge and your own intuition into it. But for this video, just to make it more accessible for non-MMA fans, we're just gonna go as is. So when we're dealing with this data, we want to do a few pre-processing. So one of the pre-processing that we've added was the dummy to all the categorical variables. In this case, if we actually look at the prep option, we can see that we're just applying the dummy variables to the weight class, and that's fine. So it's just and I did a one-hot encoding just because I prefer one-hot encoded features, but you can always do a dummy if you want. But for the models that we're going to be using, I think one-hot encoding makes the most amount of sense. So if we check our columns, we have 293 columns. That is a lot of columns, and we need to figure out, what can we do to reduce that? Just even before we even start modeling it, we know that that's a lot of features, and probably 9 times out of 10, we know we don't need this many features. Okay, so for the basic dimensionality reduction, we can kind of just do what we already know about. So one, we obviously add the mean imputation because we can see that the average reversals have some missing values, and that's a problem with my scraping script. Generally these NAs should be 0, but I know with the average reversals, I'm fine with just imputing the mean. I could also do median if I want to, but that's not really going to do anything crazy. One thing that I will say is we should also pretty much always include a step near 0 variance. This will remove like any columns where all the samples kind of share the same value. So I did near 0 variance. Also try to remove any linear combinations, just to see if that'll remove some of the columns. And then also did apply the generic dummy features. So we're just still going to do the dummy on the weight class. And as you can see, we went from 293 columns to 198, which is actually pretty good. We managed to remove like almost 100 features just right out of the bat. So this right here is something that is pretty useful when we can just remove redundant stuff. And it's something, if we don't have a lot of features, maybe consider not doing it. But if we do have a lot of features, it's generally pretty easy and pretty free for a resource standpoint to just do the near 0 variance linear combinations to remove any columns that we think that the model wouldn't really get any information of. Another thing that we also can include is step core or correlation. And we're basically removing any highly correlated features. One thing I also could say with the step correlation is that I think the default is like 70, or it's 90. We can change that threshold with a simple tune. So if I wanted to do threshold, and I can say tune, and I can say like core tune, right? And then we can throw that into our grid, and then we can tune it based off that, which would add a little bit more granularity into our actual models, so we can figure out what we want to actually remove. So with the actual correlation filter, we managed to remove even more features, right? So 136, so 198 minus 136, just because I don't feel like doing math, is 62. So we additionally removed another 62 features, and we were able, from comparing our baseline with no feature dimensionality reduction, we've removed over 100 features, which is always really good. But if we think about it, a lot of our features should be kind of correlated together, right? We're using these moving averages, which should be kind of related towards our other AR, our other moving average features. So we have like a weighted moving average, a moving average that uses two of them, two of the previous fights, a moving average that uses three of the previous fights, like a moving average that uses all of the previous fights. So we can see that those variables should be pretty correlated together. So what I actually want to do is kind of look at these correlated features and just figure out like which values are just like the most correlated. So right here, total takedowns absorbed and total knockdowns absorbed are highly correlated, right? They're 1-to-1. And we kind of know that because if you get knocked down or if you get a takedown, it could be a knockdown too. Same with like total strikes, a fighter's total strikes avoided and a fighter's total significant strikes avoided. We know that strikes and significant strikes are basically 1-to-1 correlated because if you throw a significant strike, it is still counted as a strike. And that's something where, maybe we don't want to remove those features because we know that total strikes and total significant strikes are a little bit different. And we may want to just prioritize total significant strikes instead of total strikes, right? So we can kind of see here that, again, most of our correlated values are pretty high, right? So it removes a lot of it. What I also want to do is kind of just plot out a histogram of the actual correlated values for all the features. I also will say that I did a little filter just so we can remove any redundancies. So like pairwise pairwise features. So it kind of just keeps the first, subset or first like combination. So we see that, I have pretty long tails towards the upper ends where I'm sure that the correlated features filter just kind of did a little cut right there and said we're removing all that garbage. Okay. So one other concept too that I think is pretty popular is like just use a PCA, principal components analysis, and that can basically turn all these correlated features into these components, and then we can use our model to just keep on chugging. PCA linear regression I think is pretty popular. I will say I think Max Kuhn says that he doesn't really get a lot of value from it, probably because I think he comes from like a pharmaceutical background. Where all these like correlated structures are probably important, but I am definitely not in chemistry. I'm not a chemist or in big pharma, so I definitely don't know, but I'm sure he has his reasons why. But what's cool about step PCA is that we can kind of change a threshold, or we can specify specific components. So we can kind of manually determine the actual amount of features we want to use, or we can have some type of rule-based system where we can say we want the components to explain at least like 75% of the variance, or maybe if we can increase it, knowing that that'll also be related towards the number of components created. Right, so if 0.75, if we just say 0.9, see we basically double, we more than double our features, but it's still 60, which is better than the rest of our actual pre-processing methods. So one other way to actually address high dimensional correlated structures is just use a model that can kind of handle that. And for me, when I think of like high dimensional data, I definitely think about, like a tree-based model. So you can just use your simple decision tree from our part. Just tune the tree depth, make sure that we don't have too deep of a tree. Also make sure that we have a decent amount of samples in each little node. And we also can tune our cost complexity too. Right? So I generally will never use a simple decision tree. Maybe if I'm doing an ensembling or stacking of a bunch of machine learning models, but in real life, decision trees or the basic R-part decision tree is not very useful from a pure predictive standpoint. I think there's a common phrase where, the only problem with decision trees is that they're not good at predicting things. And I think that's pretty true. That's why we have these ensemble methods like random forest and XGBoost. So again, with these tree-based models, obviously, like for me, I'm always using random forest or XGBoost models. I definitely use way more random forest models in my own work, but XGBoost models are totally fine. And for some reason, I do have like an inclination to use XGBoost models with regression problems, but I don't think XGBoost is like specifically better in regression versus classification problems compared to random forest. I think just in my limited work that I've noticed, I've just leaned towards random forest. One of the main reasons why I actually catered towards more of random forest model is even though they have similar performance, and I think realistically XGBoost model will have a slight edge in some cases, especially with these like analyses or post hocs of machine learning competitions. But one of the reasons why I like random forest model framework the best, or the random forest algorithm, is that we have way less parameters to tune. We just have min n, number of features that it samples, and the number of trees. Whereas with XGBoost, we have trees, number of trees, tree depth, learning rates, stuff iterations, all that stuff, which can be very useful, especially with the stop iterations. But for me, let's keep it simple. Just tune 2 of these parameters that's available. We know that M tree is basically uses the square root of the amount of features available, I think. So that's kind of that's like the basic rule, I believe. So we only have like 2 parameters to tune versus where XGBoost, where there's way more parameters to tune, which can cause a lot of issues. So once we have a tree-based model, I think if you don't want to use a tree-based model, you want to use like like a k-nearest neighbor model, or linear regression, we can actually do like a basic manual inspection using variable importance. And right now I just create a random forest model with 500 trees, baseline parameters, but we can also set the importance to impurity, and we can just fit it to our trained data. And using the VIP package, we can get a little nice plot of what the model sees as the very important features that it uses for predicting things. And we can kind of see that, yeah, if we're trying to predict strikes landed, the fighter sig reg mixture is basically like the proportion of significant strikes to strikes. So if they have a high mixture of significant strikes, I'm sure it has a nice predictive capability to predict strikes landed, right? So we can see it, it's using a bunch of strikes, significant strike metrics. It's also using the opponent's significant strikes and strikes metrics. It's also looking at the takedown percent. So, for me, thinking about it, like maybe if they have a lower or higher, maybe if they can threaten the takedown more, they're more often just keep it standing up and just fighting, which will lead to a higher strikes landed. And then finally, we can see that ELO, or our ELO score, it plays some importance, and that's pretty good, because if we think about it, if a fighter has a high ELO or has beaten a lot of very good fighters, they're probably pretty good at striking. Generally, champions are pretty good at striking. So that's something, again, that we'd expect. And if you know a lot about MMA, or you just kind of know a little bit about MMA, and you can use some of these features, you kind of like intuitively determine like, okay, we don't really need those ARMA features. We kind of just care more about these mixtures and percentages. We know that we finally know that, like, oh, it actually takedown is pretty useful. So maybe we can go back, maybe do some takedown. We can create some takedown features and rerun this thing and just see what it's also trying to do. Again, I definitely would try to avoid like data leakage. So try to keep it on the trained data and stuff like that. In this case, we're just juicing our trained data using our baseline recipe. Okay, and finally, what we can do is we can kind of do the brute force approach, which is recursive feature elimination, where it basically goes through and iterates and chooses what features to use, takes them out, and then we can assess really what the model sees that deems a important feature. So we're kind of using a model to basically select the features for us. Obviously this is very great because we can kind of have a more systematic approach to it that also has more of a structure to it instead of using our own intuition. There's more of a science than an art. But one of the main issues with recursive feature elimination is it really is like the brute force approach to dimensionality reduction, where we can it's going to take a lot longer, and additionally it could cause a lot of overfitting, or it could just choose some features that maybe it didn't make any sense to just so happens to be having a strong relationship to our target variable. So what we're going to do though is we're going to just define our baseline model, which will be like selecting our features, and then we can create our basic recipe, and then we can add our step select VIP. So instead of us kind of going through the VIP plots and looking at, the variable importance and just filtering it by like 0 and just kind of reading it, we're going to have the model basically kind of go through it and do it itself. And then we can set our own threshold by like doing some tune function. So we're actually going to run this, and we're going to apply the recipe to it, which is going to actually remove all the features that the model sees is not useful. And now we can kind of compare it once it runs to what our manual inspection with our variable importance versus this one. I will also say that we use different importance rules. So instead of permutation, we used impurity. So that's another thing that we can consider is, what type of importance should we use for our variable importance measurements. So we're going to let it go. And see, again, right now it's taking a decent amount of time to actually run the recursive feature engineering or feature elimination, but it is pretty useful. While we're going to wait for this to load, I'm going to go through the actual recipe selectors package. It's still in development, so you have to do like an install GitHub, but it's very useful, especially since it's adding a lot of the feature elimination methods from Caret. And I've only gone through the step VIP, but there's also like step select crosstab, there's an ROC, there's maximum relevancy, minimum redundancy feature selection, there's info gain. So there's a bunch of other methods that we can do. In this case, I'm not really familiar with all these things. I'm familiar with like ROC, crosstab, and VIP, and I guess information gain, but like step MR, Baruda, and Car score is something that I'm not very familiar with, but it's something they also consider to use. Okay, so if we actually look at this, compared to our filtered VI variable importance, where we say anything that's above 0 or like not important will include, we can see that we have 26 features versus essentially 30 features, because it's still going to include the outcome variable. But we can see what it's saying is like, again, sig strikes, this strike mixture is pretty useful for our model. But we also notice that, it's also including ELO and opponent stuff, but it's not including as much opponent data, right, than we would expect. So it's like total strikes absorbed, total strikes avoided, received. So it's kind of measuring like, a person or a fighter's strike metrics with the opponent's defensive and offensive strikes metrics. So as you can see, it's a very useful thing. It's very strong, but we know that, we're missing, it's adding a few things that, maybe we think it might be redundant, etc. So that's basically it for this video. I know this is a pretty quick video. I actually recorded, I'm recording this video right after my starting video on Docker back to back, just because I have some free time this weekend to work on it. So I figured I'd record them back to back just to, free up some time. But honestly, I think these methods right here are some very good starting grounds for what you want to do when dealing with the highly dimensional features. I haven't gone over like dealing with categorical features with a large amount of levels and utilizing embeddings and stuff like that, but I think that'll be for a future video, especially for like text analysis. So with that being said, I hope you guys enjoyed the video, and I'll see you guys next time, and tidy on.